Good morning, sir. Myself, N. Devi. I am from ECE. My roll number is 234310432, and today my topic is uniform linear arrays. First, introduction to uniform linear arrays. A uniform linear array is a type of antenna array with elements evenly spaced along a straight line. It is widely used in applications like radar, sonar, and wireless communication for detection finding. To uniform spacing simplifies the analysis and design the arrays beamforming capabilities. Antenna array are used to achieve higher directivity and control beam direction. A uniform linear array consists of identical antenna elements arranged in a straight line. Next, basic structure of uniform linear array. A uniform linear array consists of multiple antennas elements aligned in a straight line with equal spacing. The number of elements and their spacing are key parameters influencing performance. Typical element spacing is often set of half of the wavelength to avoid grating lobes. Elements are placed at equal distances, usually d is equals to lambda by 2. Each element radiates electromagnetic waves with a specific phase and amplitude. The overall radiation pattern depends on the spacing and phase difference between the elements. Next, array geometry. The geometry of the ULA is characterized by the number of elements and the inter-element spacing. The array length is approximately n minus 1 times and the spacing d. The linear arrangement allows for straightforward mathematical modeling of the array response. Array geometry refers to the physical arrangement of antenna elements in an array system. The geometry defines parameters like beam width, directivity, and side lobe levels, directivity directly affecting the overall radiation pattern and the system efficiency. Next, array factor. The array factor describes the combined effect of all antenna elements, signals, and their phase differences. It determines the overall radiation pattern of the array. The array factor is crucial for understanding beam steering and directivity. And here the formula for array factor. It's also determine the shape and direction of the radiation pattern. It depends on the number of elements, spacing, and phase difference beta. Next, beam forming in ULA. Beam forming involves adjusting the phase and amplitude of the signals at each element to steer the main beam. Digital or analog techniques are used to achieve effective beam forming in ULAs. Beam forming is the process of combining signals from multiple antenna elements to focus radiation in a specific direction. Enhances signal strength toward the desired direction, reduces influence, and improves signal to noise ratio and the system efficiency. In a ULA beam, direction is controlled by the adjusting the phase shift or time delay between elements, main lobe and side lobes. The main lobe is the direction with the highest radiation intensity in the array pattern. Side lobes are similar to Side lobes are smaller peaks that can cause interference and reduce system performance. Proper array design aims to maximize the main lobe and minimize side lobes. Beam steering. Beam steering is the process of directing the main radiation beam of the antenna array toward a desired direction without physically moving the antenna. Achieved by introducing a progressive phase shift or time delay between antenna elements in the uniform linear array. In modern system, electronic phase shifters are used to instantly change the beam direction, providing fast and precise control, allows real-time tracking of moving targets, improves signal coverage, and reduces interference. The scanning range is limited and improper phase control can lead to the grating lobes or distorted patterns. Extensively used in radar systems, smart antennas, sonar, and 5G based stations for adaptive communication and target direction. Grating lobes and spacing constraints. Grating lobes are unwanted peaks in the radiation pattern that occur when element spacing exceeds half a wavelength. To prevent grating lobes, the element spacing should be generally less than or equal to half of the wavelength. Proper spacing ensures a highly directivity and reduces interference. Advantages of ULA. ULAs have simple geometry, making analysis and implementation straightforward. They enable precise control over beam direction through phase adjustment. ULAs are scalable, allowing for increased directivity with more elements. Provide stronger radiation or reception in a specific direction, improving signal strength. Easy to model mathematically due to uniform spacing and linear geometry. Performance can be enhanced by simply increasing the number of elements. Limitations of ULA. These are the limitations of ULA. ULA are susceptible to mutual coupling effects between elements. It elements spacing exceeds half wavelength, unwanted radiation loops appear causing interference. Small errors in element placing or phase adjustment can significantly affect performance. Applications of ULA. ULAs are also utilized in sonar and radio astronomy for high resolution imaging, utilized for beam focusing and scanning to produce clear diagnostic images. ULAs are used in radar system for target detection and direction finding. Summary. Hence, we conclude that a uniform linear array is a linear array uniformly spaced antenna of elements used for directional signal processing. The array factor and beam widthing techniques are fundamental for controlling the radiation pattern. Limitations involve grating lobes, mutual coupling, limited scanning range, and precise phase control requirements. Thank you, sir.